who will give her second lecture on topological Hochschild homology and topological cyclic homology.
Thank you very much. So after my lecture yesterday, I enjoyed a really nice discussion with some people from the audience who were asking questions about what I talked about, which made me realize there were a couple of things I wanted to make more specific. So I started by talking about K-theory of rings and Hochschild and cyclic homology of rings, and then moved on to talking in a somewhat vague way about ring spectra. And they were saying, well, what's the connection between the two? And I realized I should have made it more explicit. So just as a couple of comments on the previous lecture, just to clarify a few points and to make the connection better between the classical situation and the homotopy theoretic situation. So quite informally, and I can make this more formal by the end of this hour, we have a way of starting in the category of rings and really, in some sense, embedding that into the category of ring spectra, that is to say, algebras in some appropriate monoidal category of spectra. So you can start with a ring R and associate to it what's called the Eilenberg-MacLane spectrum, which is the spectrum that represents cohomology theories with coefficients in R. And so using this way of embedding rings into ring spectra, you can say, OK, I can take my ring, I can look at it as a ring spectrum, and I can apply some of these spectral invariants, THH, TC, and so on, and obtain new invariants of the ring R. And one thing to know about this Eilenberg-MacLane spectrum is if you look at its homotopy groups, you're going to get R back. So that's you can do. And then one more comment I wanted to make was that I was a little bit too hand-wavy in the way I presented the Bergstedt spectral sequence yesterday. It made it look a little bit too easy. So I have two comments about the Bergstedt spectral sequence. So the Bergstedt spectral sequence applies in the case when you have a commutative ring spectrum. And when you have a commutative ring spectrum, it turns out that THH of that ring spectrum you can really see as tensoring up with a circle in some sense. This was related to a question that was asked yesterday. And you can get a filtration of that object by looking at a sort of natural skeletal filtration of the circle. And that is essentially the filtration that's going to give you the Bergstedt spectral sequence. So I just wanted to mention that in passing, but also to say that what you're going to have in this spectral sequence, if you look at, let's see, I'm going to make a mistake about the indices being up and down. Never mind. It's going to converge from ith Hochschild homology. So in the case, let's apply it just to the case of HFP, which is what I was talking about yesterday in the example that led to Bergstedt periodicity. So in this case, we're going to look at HFP. Its homotopy groups give us FP back. So we have a spectral sequence that's converging from HI of FP, but somehow with coefficients in the homotopy groups of the sphere spectrum, the homotopy groups of spheres. This is a very complicated ring. So there's a lot of complication built into this spectral sequence. And then it's converging to, so this is somehow with a J there, pi ij. So it's a lot of complication going on. It looked a little bit too easy the way I set it up yesterday. OK, so that's just a couple of comments to explain how we can see this homotopic theory here as an extension of what we have for commutative in the classical case, and a little more information about this spectral sequence. And this spectral sequence also helps us to understand, give us an example of a case where THH of a classical ring, so we can see this as THH of FP itself, is actually different from the Hochschild homology. OK. But now I'm going to delve into more detail about some of the things that I presented in an overview yesterday. So part 2, now I'm going to talk about ancient history. And a good reference for this ancient history is this book of Lode's on Hochschild homology and cyclic homology. Okay, so the point is that now we're going to start with a category that I'll call, so if I'm going to fix K a commutative ring in the completely classical sense of the word. And I'm going to look at a category that I call alg_K, which is the category, in this case, of augmented, either non-positively or non-negatively graded, differential graded algebras. So and if I were really going to go sort of do like Neolithic history, then I would even drop the DG and just talk about, this is K algebras, talk about ungraded algebras, but we can actually think about these things as DG algebras without too much extension. And so I'll remind you of the construction that we have. So for every algebra, we have this Hochschild construction that I was describing yesterday, which is now going to be a simplicial K module. Like this. And where in degree n, this is just n plus 1 tensor powers of A. And as I explained yesterday, the face maps are given by multiplication, and we just wrap around for the very last face map. One remark while I say this is that I didn't write this explicitly when I was talking about THH yesterday, but it's exactly the same with THH, that the face maps in the THH simplicial construction were also given by multiplication, or this sort of cyclic action plus multiplication. So it's always the same kind of structure. Now, what I'm going to think of, I was a little bit hand-wavy and not very specific about this yesterday, but today I'm going to think about the realization of this simplicial object actually as giving me a chain complex. So this is now going to be a chain complex over K, like this. And one can even be very specific about what it is. So as before, I'll just call it HH of A. And what is it? It's actually an ordinary tensor algebra. So a copy of K plus some sort of large direct sum of copies of the augmentation ideal, powers of the augmentation ideal, because we're starting with an augmented algebra like this for n greater than or equal to 1, plus a differential that's encoding the multiplication operations. Yes, yeah, my rings have identity. Exactly, the degeneracy is just using the unit map of the algebra. Absolutely. Thank you for the question. So we get this construction, and this is something which is actually relatively easy to understand. Now, here's an exercise for you. Well, it's a little bit of a cheat because I didn't actually give you the differential explicitly, but you can figure it out based on what happens when you apply Dold-Kahn to go from a simplicial module to a chain complex. But little exercise, which is that if A is commutative in the graded sense, so I multiply an element of degree K times an element of degree L, I can flip the order, but there's a sign that's introduced, then this thing is also naturally, in a relatively straightforward manner, also a commutative algebra. So first you have to show that there's some kind of multiplication, because that's not obvious on this construction, but in fact it is commutative as well. Okay, now I'm going to make a digression. Because of an important connection there is between Hochschild homology and free loop spaces. And this is going to be, understanding what's going on with these free loop spaces will actually be helpful for understanding what we want to say about cyclotomic structure later. So there's a theorem which is due in various parts to Bergelian Fedorovitz. And I'm forgetting Jones. So I'm putting together here results that come from a number of different papers where he said, let's start with a topological space. So we're changing gears here. So let X be a topological space. Then there are two ways we can associate a differential graded algebra naturally to the space X. If we assume that X is pointed, then we have a choice of base point, then we can think about the base loops on that space. And the chains on that base loop space is a differential graded algebra. So you could say, what's the Hochschild homology of that particular differential graded algebra? So if X is pointed and connected, then it turns out that the Hochschild homology of the differential graded algebra given by the chains on loops X is isomorphic to the homology of the free loop space on X. So here, let me just write it here. The free loop space is just a space of maps from the circle, maybe I'll just call it T again, into X. So this is a place that has a lot of interesting structure. It's very interesting to study for a whole bunch of reasons. And now we see a connection between Hochschild homology of this particular DGA and the homology of the free loop space. But there's another way that we can associate a differential graded algebra to a space, which is to consider the cochain algebra on the space. And so it turns out that if X is 1 connected, then the Hochschild homology of the cochains on X is isomorphic to the cohomology. And here just be a little bit creative with degrees being negative and such, but anyway, that's what it amounts to. And so cochains on X is almost a commutative algebra, well, almost. And it turns out that this thing is actually an iso of algebras, because we have an algebra structure in the cohomology, of course, and this is due to Ndombal and Thomas. So we see this nice close connection between Hochschild homology and the homology of free loop spaces. So what can we say? Maybe there's something about the structure of free loop spaces that we can expect to see reflected in Hochschild homology. So let's see what we know about the free loop space. These are things that are relatively easy to check that we might then hope to see reflected in Hochschild homology. Well, the free loop space naturally admits an action of the circle group, just the way the Hochschild homology is going to, because it's the realization of something cyclic. But we can describe it very explicitly in this case. If I think of T as being given by a specified element of T by the angle that it makes, then we take a pair like this to the path. So you just shift everything by lambda. You just rotate. Rotate the loop. Okay. That's nice because that's also something we see in Hochschild homology. And if we restrict the T action to the cyclic group as represented by the nth roots of unity, then what we see is that we get an action of the cyclic group on the free loop space. And moreover, if we calculate the space of fixed points of this action, we end up with something that's actually homeomorphic to the free loop space itself. If I take this space and look at the space of C and fixed points, I get something that's homeomorphic to Lx. So I'll make this not hard. Just to see that. So that's really special that we can do that. And this is the sort of structure that we're going to see reflected in the cyclotomic structure of THH. OK. So is there anything more I wanted to say about free loop spaces? So one more thing that I can say is that because of this action of T, of the circle group, on the free loop space, we can be interested in computing the homotopy orbits of this thing. So if we wanted to compute the homotopy orbits of the T action on this free loop space, then one way to do that is to say, well, I'm going to use this. So I have a circle action. I can sort of tensor over the chains on the circle, which is now a DGA, and this guy is a module over this DGA. And then here I could have the chains on the classifying space of T. Contractible space with a free T action. And when I do that, it turns out that this reduces to something quite simple. You can get a model for these homotopy orbits by just starting with the chains on the free loop space and then sort of twisting in. So I'm going to put a little tilde over the tensor product to say that what I'm doing is I'm taking a tensor product of this guy with now a polynomial algebra on a generator of degree 2. So these are twisted together, which means that as underlying graded Z modules, it's just the ordinary tensor product, but there's the differentials interact. So this guy is sitting inside this one as a subcomplex, and then there's this differential here that's sort of twisting things together. And the point is, where does this come from? The point is that this, excuse me, is, oh, sorry, this isn't the classifying space, it's the classifying bundle. Here we really get the classifying space. The homology of BT, which is to say CP infinity. And so it's just enough to look at to twist in this little extra generator coming from the homology that has to do with the formality of this whole situation and so on. So we get this very nice small model for the homotopy orbits. And we're going to see something like that as well when we talk about cyclic homology in the case of Hochschild homology. So if we look for inspiration from what we just noticed for the free loop spaces, so the cyclic structure on this guy, we can have a cyclic action on each of the terms. This gives us, as I said, an S1 action on the realization, which we can see as follows. And we can build an entirely analogous complex perfectly analogous to what we were doing there, which has the following properties. What's the differential actually doing if I have a tensor product like this? It's going to apply first the ordinary Hochschild differential, which is coming from the face maps of the simplicial gadget, tensor with VK. And then I'm going to be a little bit lazy with signs. It does what's called taking the norm. And norm, I realize, is an overused word in mathematics, but this is called the norm here as well, for a fairly good reason. Tensor with VK minus 1. So what is this? This is going to be a signed sum of cyclic permutations. So here we see the cyclic action showing up in this term that has to do with what the effect of tensoring with VK is. So this thing is the cyclic complex. Yeah, that's a definition. I mean, there are various ways one can define it. One can define it using their sort of bicomplexes and so on. But I think that seeing this really as, you can see it very explicitly as coming from this S1 action in this way. And this really is the cyclic complex of A. You can take it as a definition. So one more thing I want to say about this. Two remarks about this. One is that we have there's a short exact sequence of complexes that looks like this. So HHA sits inside HCA, just as the chains on LX sits inside those homotopy orbits. And then there's a map here to shift by 2. So this is just an inclusion. And this one is taking a word A0 tensor A and tensor VK to the same word in the A's, tensor VK minus 1, whence the shift of 2 there. And this, the associated long exact sequence, is what's known as the Kohn long exact sequence relating Hochschild homology and cyclic homology, which is much used in order to make computations. So that's one remark. The second remark is that we have a connection between this Hoch cyclic construction and free loop spaces again, sort of unsurprisingly. If I calculate the cyclic homology of sorry, I'm putting this in the wrong order, of the chains on loops X, so that's giving me a DGA again, that this thing is actually isomorphic to the homology of the homotopy orbits. So this analogy continues on to the geometric level. Now, one thing that's important to know about Hochschild homology in this context is that we can extend it from looking at differential graded algebras to looking at differential graded categories. So the point is that a differential graded category is nothing but a differential graded algebra with many objects. In a sense, it can be made very precise. And so one can extend this as follows. So here I think I should cite McCarthy because he, I think, was the first to extend to exact categories. There's work of Keller. There's work of Toen. And I'm probably forgetting some people to whom I apologize. Taboada, perhaps. So if A now is an augmented DG category, so we have a set of objects, and between every pair of objects, we have a chain complex of morphisms, and the multiplication, the composition of this category by tensoring these morphism categories, and there's a map from tensor categories like that. And so augmented just means that if I fix an object and I look at the chain complex of morphisms from that object to itself, then there is an augmentation from that down to K. So this is OK. All right, so in this case, then we can again construct a simplicial object in the category of DG categories as follows. Well, I need to tell you, first of all, in every simplicial level, I'm going to have a DG category. So what are the objects? In level n, the objects are the same as the objects of A, so the objects don't change. what changes. That's what's going on with the morphisms. And so if I have A and B, which are objects of A, and I'm looking at what the morphism chain complex is from A to B, then I get that by looking at all sequences of objects, starting with A and ending with B, and the associated morphism spaces. So I look at all sequences, A equals A0, A1, up to AN, which is going to be B. And I look at the morphism spaces, A0, A1, tensor over K, to AN minus 1. Sorry. I wanted N minus 1 to be B, sorry. Those have too many terms. And N minus 1, and then back to A0. So I should maybe put the second one in here. It's A1, A2. So it continues like that into the last one where you sort of shift around. And the face maps here come from doing the compositions pairwise. And at the very last face map, you're going to take a morphism here from AN minus 1 to A0 and compose it with a morphism from A0 to A1. So it's exactly analogous to what we were doing in the DG algebra case. So face maps correspond to composition. And you can, again, do a geometric realization and end up in the world of DG categories. And yeah, so HH0 is just going to be the category itself. Right, so HH... oh, maybe I'm off by something. Let's see. That's N. Oh, yeah, you're right. It should be N. Yeah, sorry. Well, because it's a coproduct, in this category, the coproduct is direct sum. So it's the same thing. Let me just fix this. Thanks, David. OK. So one reason to make this extension is it allows us to formulate some important properties of Hochschild homology that we couldn't really even formulate if we hadn't made this extension. So some properties, and this was, the first one is called agreement, first established for exact categories by McCarthy, extended to DG categories by Keller. It says that if I take A, which is a DG algebra, then I can consider the DG category of modules over this algebra. And it turns out that if I look at the Hochschild homology of A, it's actually isomorphic to the Hochschild homology of what one might call perf A. Where by perf A here, what I mean is, so these are DG modules. These are things that are built up in a quasi-free way, finitely, from A itself. So there's some sense perfect or compact or DG-free is what Keller calls them. They're basically perfect. So we have this kind of agreement between the Hochschild homology of the algebra and of some appropriate category of modules over the algebra. There's also right. So good question. Let's see. I think, let's see. How do we understand that? The question is why, OK, this is I should have thought of this. The question is why this isomorphism makes sense, why these things live in the same place. Because this thing is the homology of a chain complex. And this thing, is, as I've written, is the homology of a DG category. So we have homology object by object. I think, let me get back to you on that. I should have thought about this. OK, sorry. I'll get back to you. Oh, I'll get back to you, sorry. I don't want to say anything more ridiculous than what I already said. So we'll put a question mark there, and I promise there'll be an answer tomorrow. OK, meridian invariance. So one form of this, there are various forms of meridian invariance for Hochschild homology. One form of it was developed by Toen, who showed that if I'm looking at DG categories and I have what he calls a Moridi equivalence. So Moridi equivalence means basically that, again, when you restrict to sort of a perfect subcategory of these categories, then you actually have an equivalence. Then this implies that their Hochschild homologies are isomorphic, and at least they live in the same world. So this actually makes sense. And then we also have, and I'm not going to write out specifically what it means, we have versions of additivity and localization. OK. One last remark, I'm not going to write anything too specific about this, is that in this context, you can actually give a pretty explicit description of the Dennis trace map. So just say it like that. So we have a very explicit construction of a Dennis trace map from K-theory to Hochschild homology. You don't just have it there exists because we have a universal invariant. You can really sort of see what's going on with the Dennis trace map in this case, in at least two different ways. Actually, a good reference for this, there are some notes by John Rogness that one can find online about trace maps and such, where he provides two nice descriptions of this trace map explicitly. OK. I think that's enough ancient history for a very modern conference. So we'll take at least a small step forward and talk about the brave new algebra context. Sure. I used it really in order to have this explicit description of the Hochschild complex, really, in terms of the augmentation ideals. It's a way of, yeah, exactly. So if we look at the brave new algebra aspect here, so I'm well aware that a lot of the audience is not made up of people who work with spectra on a daily basis. So I'm going to spend some time introducing the framework. And there are many ways one can go about introducing algebra in stable homotopy theory. I found that actually the way that Thomas Nikolaus and Peter Scholze set it up in their paper was really nice. It's based, as they say it's based on a description by Stefan Schwede. And I also found it helpful to look at course notes by Andrew Blumberg. So he has course notes online from a course on equivariant homotopy theory, which I can warmly recommend. All right, so what's the basic category of objects we're going to be working with? So I'm going to make a specific choice of the kinds of spectra that we're going to work with. They're sort of particularly nice to work with when you want to introduce group actions as well. But they're far from the only possible model for stromal homotopy theory. So there's a category that we're going to call SPO, the category of orthogonal spectra. Oh, and one remark I should make is that all the topological, for those who are following the details, all the topological spaces I'll consider be compactly generated. Weak Hausdorff. So there are various point-set topological issues we don't have to worry about. So we're going to consider this category. So what are the objects? The objects are sequences of pointed spaces. So X is a pointed topological space together with some structure maps. So the specific maps themselves are part of the structure. They're not just properties. So there exists, we have a continuous base map, or base point, let me say action. So I'm going to action of the orthogonal group on Xn, which preserves the base point. So here's the orthogonal group. So it has to preserve the base point. And then I also have these maps I've described very briefly yesterday that are relating the nth space in the sequence to the n plus first via the suspension. So you have as well for every n continuous base map. Let's call this rho for the action. And this one is going from Xn smashed with the circle. So I'm really thinking of the topological circle here. So this gives us the suspension, Xn, 2Xn plus 1, like this. Let's call that sigma n. And there has to be a certain compatibility between the orthogonal group actions and these suspensions, which we specify as follows. Right. Such that if I start with Xn smashed with an M sphere, well, I can look at that as Xn smashed with S1 smashed with Nm minus 1 sphere, apply sigma n, and end up in Xn plus 1, and so on, all the way down to Xn plus m. And this composite must be On cross Om equivariant. So this is obviously On cross Om space because it sits in On plus m. Here On is acting, here Om is acting, and this has to be On cross On, m equivariant. And then the morphisms are what they have to be. So maps of sequences that preserve the structure. Okay. Exactly. Exactly. Yes.
Is everything just up to homotopy here?
This is strict. This is strict. Yes. Because we haven't defined it. Well, we could talk about homotopy of spaces. But now we're going to do just homotopy of spectra. All right? What is what? Sorry? the use of orthogonal spectra. We can actually put a model category structure on here. So we have weak equivalences, cofibrations, vibrations. And if you look at the associated homotopy category or infinity category, then we're going to get the actual what's called the homotopy category of spectra. So this is something that was defined, that you can find sort of a homotopy theory of a stable, it's the stable homotopy category. So it's a way of thinking about homotopy theory where you allow yourself to invert suspensions. So you say, okay, what is preserved about topological spaces up to inversion of suspensions? And this category captures that kind of information. Okay? Thank you for your question. All right, so we have to make some more choices here. We have to define homotopy in this category. So if I have an orthogonal spectrum and an integer, I'm going to define the kth homotopy group of this spectrum as follows. So the kth homotopy group of X is defined to be a certain colimit. Well, I look at all of the groups pi k plus n of xn. So those are all well defined. Those are homotopy groups of ordinary spaces. And the suspension maps turn this into a directed limit. We take this directed limit, we take the colimit over all n's, and that's what's left. That's sort of what is not inverted by suspension. That's what we're picking up here. Okay? And then we're going to say that an F, which is a map of orthogonal spectra from X to Y, so this is my notation for a morphism in the category of orthogonal spectra from X to Y. This thing is what's called a stable equivalence. If it induces an isomorphism on these stable homotopy groups. So if pi k of F is an iso for all k. All right? So I think I owe you some examples of such things. So there are two examples that I mean, there are lots of examples one could give. I will give only two. The first one is the sphere spectrum. So this is just the sequence of spheres. Each sphere has an obvious ON action, and there's an obvious map from the suspension of Sn to the Sn plus 1. What about the base point? So that's a good question. So the actual model of Sn that we're considering is a compactification of Rn. So the one-point compactification, and we're considering the point of at infinity to be our base point. Okay? So there's a very specific model in mind here. So this is the sphere spectrum. And a little variant on that is when we take the suspension spectrum of a specific space. So if we start with X, which is a topological space, then we can either, you can start with a topological space or a pointed topological space. Let's start with a space with no specific base point. Then you can form what's called the suspension spectrum of X. You put a little plus down here to say you're going to throw in a disjoint base point. And so this is a sequence. Plus is my disjoint base point, like this. And it has, again has an ON action and an obvious map between the suspensions. Okay, so that's called the suspension spectrum. All right, well, it turns out that you can equip this category of orthogonal spectra with a monoidal structure that is usually denoted smash, and which we can think of as in some way that I'm not going to make specific today, tensoring over the sphere spectrum. So I don't know, call it a remark or a theorem perhaps. There is a closed symmetric monoidal structure on the category of orthogonal spectra, so that we will denote like this. SP0, there's a smash, which is going to be our tensor product. The unit is going to be the sphere spectrum. And then we have some sort of mapping space object, which is usually denoted by F, like this. OK. Now, because actions of finite cyclic groups and actions of the circle group play such an important role in our discussion of Hochschild homology, topological Hochschild homology, and cyclotomic structure, we need somehow to work group actions into this picture. So we need to add group actions, equivariant structure. In order to be able to make any sense of some of the things I was talking about yesterday with these fixed points and so on. Okay, so how are we going to do that? Well, let's start with the case of a finite group, and then we'll treat the only infinite groups we really care about, which will turn out to be the proof ring and the circle group. Okay, so let G be a finite group. Then we're going to define a category of G orthogonal spectra as follows, or orthogonal G spectra, better said. So G SPO is the category of orthogonal G spectra. So how are we going to build a G action into here in a reasonable way? Well, we're just going to do actually kind of the most obvious thing you could imagine is to consider just sort of objects in this category of orthogonal spectra with a G action, which we make formal as follows. So G SPO is the category of functors from a category that's often denoted BG to SPO. So BG has one object and the morphisms, the endomorphisms of that object is just G. So that's one clean way of understanding objects with a G action in a particular category. So this seems quite straightforward. So this is, again, it inherits a closed symmetric monoidal structure where the G acts diagonally in a smash product, for example. And it's also what we say tensored and cotensored over pointed G spaces. So tensored and cotensored means essentially I'm going to take a spectrum, I'm going to take a G space, or sorry, I take a G spectrum, I take a G space, and then I can smash with that pointed G space in each level, and I'm still going to have a G orthogonal spectrum. Similarly, if I have an orthogonal G spectrum and I have a space, I can do point G maps in at every level, and that gives me what's called the cotensoring. So it's a way for the pointed topological spaces to act or coact on this category.
What does it mean for a symmetric monoidal structure to be closed?
Right, so basically you have a hom, right? So if you look at smashing with a fixed object, it admits a right adjoint, which is homming out of that same object. Okay? Anything else? Okay, so we have this category, and in the case of, so it's a category of spectra. So looking at the functors from this category BG to the category of spectra. Okay? So to define equivalences, all right, so in the category of orthogonal spectra, there was sort of a more or less obvious way of defining the equivalences. Here we want to define the equivalences in a way that takes this group action into account and not superficially, right? We'd like to really take it into account in a deep way and consider not only the action of G, but the action of all the subgroups of G as well. And so the way we do this is by using what's called the geometric fixed points, which is a concept that is not among the most simple, I think, but we'll make an attempt. Okay, so the first step is to define the following sort of construction. Let's start with a symmetric spectrum, a G orthogonal. an orthogonal G spectrum. There we go. And I'm going to take as well V, which is going to be a finite dimensional G representation. So, and it's, not just a finite dimensional G representation, it's an R vector space with an inner product that admits a G representation. So this, to summarize, is a G representation on a finite dimensional inner product space over R. So we have those two bits. I do believe so. So given these two bits of information, I can say what it means to evaluate my spectrum on V. So originally, I have X, which is just evaluated on various n's. Now I can evaluate them on finite dimensional representations. How do I do this? Well, I'm going to start by looking at the space of linear isometries from Rn to V. Okay? And I'm going to smash that over the orthogonal group with xn. So onx on here because onx on both Rn and V. Okay, so this gives me a pointed G space. Can you see that? Yeah, more or less. All right. Given that, I can now define the mysterious geometric fixed points functor. So it's some variant on fixed points that we think about in stable homotopy theory because it actually, I mean, for a number of reasons, but among them that it behaves well with respect to suspension. So it's kind of an interesting version of fixed points in this context. So we're going to define a functor phi g, which is going to be our geometric fixed points functor, from orthogonal G spectra to orthogonal spectra. Which is defined as follows. So it's going to take a spectrum X, so G spectrum X, to just an orthogonal spectrum, which the nth term is defined as follows. So I'm going to take X and evaluate it on a very specific representation. I'm going to evaluate it on trivial representation tensored with the regular representation. And then take G fixed points. Why exactly this is the right thing to do, I'm not going to go into for the time being, but I'm going to justify this by giving you some nice properties of this thing in just a second. But before I give you the nice properties of these geometric fixed points, we're then going to say that if I have a morphism of orthogonal G spectra, that this is an equivalence. Some people might say perhaps a genuine equivalence, but let's just keep it simple and call it an equivalence. If, well, I can think of each of these spaces instead of a G action, I can think of it as an H with an H action as well for any subgroup H. Well, so if I look at what happens when I apply phi H for any H, a subgroup of G, this should be, so that's going to be a morphism of orthogonal spectra. Okay, and that for every H subgroup of G. There are other equivalent ways of defining these equivalences, but this seemed to me to be the cleanest and shortest. So why is this a nice construction to consider? I'll give you some justification now why we should care about geometric fixed points. So here, when I say this is an no, it's not an isomorphism. It's a notion of weak equivalence in this category. So we can extend this to a model structure, okay? So the point is that these things are actually part of a larger model structure on the category of orthogonal G spectra, just as the equivalences that I defined earlier between orthogonal spectra themselves are part of a model structure on orthogonal spectra. Okay, so what are these nice properties of geometric fixed points? Well, it turns out that this functor here is characterized as follows. It turns out that there's a natural map from phi g, the smash product to phi g. So if I have x and y, which are two orthogonal G spectra, I can consider in each case their geometric fixed points. There's a natural map into the geometric fixed points of the smash. And this thing turns out to be an equivalence as long as x and y are cofibrant. So nice enough in this structure. So this is equivalence if x and y are cofibrant. So when I say they're cofibrant, that means I'm already sort of implicitly extending this notion of equivalence of orthogonal G spectra to a model category structure. Similarly for this, that this morphism preserves Hochschild. So lots of interesting spectra can be built up by homotopy colimits of simpler spectra, and it turns out that this thing actually preserves these homotopy colimits. So again, this is implicitly assuming that we already have model structures, and that's a very nice property to have. And the final one I think is nice because it sort of makes the relationship between why are we calling this fixed points, other than the fact that there are fixed points showing up in the definition there. It's the fact that if I take the geometric fixed points of a suspension spectrum, so X is now a G space, then that turns out to be the suspension spectrum of the honest-to-God fixed points of X. So it really fits very nicely with the categorical notion of fixed points with respect to the suspension. And there are other notions of fixed points that I will mention more tomorrow. We have also homotopy fixed points and categorical fixed points, and they all fit together in a complicated way. But I just want to say that if we're actually thinking about, if we have an orthogonal G spectrum, and we fix a normal subgroup of G, and we look at the geometric fixed points with respect to that normal subgroup, then we can actually think of the geometric fixed points with respect to n as being a G mod n spectrum. So remark, if X is an orthogonal G spectrum and n is a normal subgroup of G, then we take the n fixed points. This can be seen as an object in the G mod n orthogonal spectra. So it retains that action there. Okay. Let's see. So I just want to do a variant of this when G is a circle. So circles obviously are not finite, but it's a very important group in our story. So what do we do to talk about equivalences in this case? We can simply set up the category in the same kind of way. So what we're going to do is say the category of orthogonal T spectra is, again, we'll write it like this. But we're going to say that a morphism F of T spectra from X to Y is an F equivalence if the following condition holds. Whenever we take F and we restrict it, we restrict the action to thinking about just the action of a cyclic group, then it should be an equivalence of Cn spectra with respect to that cyclic group. So if I'll write it like this. If F is actually an equivalence in so I look at all the possible subgroups, cyclic subgroups coming from looking at the nth roots of unity, and that gives us the notion of an F equivalence. Because we need to, in order to be able to make sense of these constructions like the geometric fixed points, then we're definitely working with finite groups in this context. Okay, so it's 10 o'clock, and I will leave you in suspense. Because what comes next, which will be the first thing tomorrow, is cyclotomic structure. Now we've put everything in place, and we're ready to talk about what it means to have a cyclotomic spectrum in this brave new algebra sense. And once you've had trouble digesting that, and we've seen how the classical THH is a cyclotomic spectrum in that case in a very difficult to digest fashion, we will pass into the beautiful world of infinity categories and see how everything gets much cleaner and nicer. Thank you. So there are ways of constructing the Eilenberg-MacLane spectrum so that you have this kind of action. So you have to be a little bit careful about how you construct it. It's not an obvious construction. Somehow you're using orthogonal action on Sn. You do that. Yeah.
We thank Professor Hess again.
Thank you.